Okay, now let's look at single slit diffraction. This is a very similar effect that we get with double slit diffraction, except just with a single slit. You can do this if you want to try it at home. Just get a really bright flashlight, take a piece of cardboard, and take a razor or X-Acto knife or something of the like, a knife. Oh, uh, take a piece of cardboard and just cut a very thin line with your knife there, and then shine your light onto it and project that light onto a screen or the wall or whatever, and you'll see this similar diffraction pattern where you get a bright spot surrounded by other increasingly dimmer spots as they go along. It's bright and dark spots. So you can try that on your own if you like. Now, um, in this figure, rays 1 and 2 travel a path difference of 0. We saw this with the double slit. So I'm looking at this ray right here and this ray right here. So when they get here, they're going to have a path length difference of 0, and they're going to be completely in phase. Whereas paths 3 and 4, on the other hand, if they travel this distance, when they come up here, they're going to be out of phase because they're going to have a path length difference that's equivalent to a half a wavelength. And that's why you get a dark spot there, because they experience this destructive interference. Now, we're not going to go through the geometry, but I'm just going to give you the expression for the dark spots. Turns out that for a single slit, A sine theta, where A is the width of the slit, A sine theta is going to equal to your path length difference, or excuse me, no, not your path length difference, that A sine theta will equal to m lambda. And this gives the positions of dark spots. So this is a little bit different than what we had for double slit diffraction, because first of all, A sine theta, that's not really your path length difference like we had for double slit. It's not that, it's a little more complicated than that, but this is going to now give us the expression for the position of the dark spots. And here, instead of allowing m go from 0 to 1 to 2 to 3, m is actually going to be equal to m equal 1, m equal 2, m equal 3. I think on your equation sheet, actually, it does say that this is for dark spots, and you can remember that m starts at 1 instead of 0 because the dark spots don't have a 0th order. We have a first order here and here. We have a 0th order for only the central maximum, right? So we're not going to have that here with the single slit diffraction. Instead, we're now going to call the dark spots the orders instead of the bright spots. So unfortunately, that's a little bit confusing, but that's just sort of the way that it is. So not much else to say about single slit. You could see a single slit on the exam, something like this, for example. This is really useful if you want to measure a very narrow width. So if you have, say, a slit in a material, or, for example, if you want to measure the width of a wire, for example, or something else that's very thin, this same effect, even though it's like the opposite of a slit, where you have an obstruction in the middle, you can use this to find the width of that hair or wire or whatever it is. All right, so try this quick test. You'll have the solution up later. Let's go ahead and move right on into diffraction gratings. Diffraction gratings are going to work exactly like double slit. All right. Diffraction gratings are very useful. You'll probably encounter one at some time if you go into any sort of scientific career, biology or chemistry or whatever, because they're used commonly in spectrometers. Very nice, easy, cheap way to build a spectrometer. Most diffraction gratings are made from some transparent material. Plastic, usually. You can make here a transparent material with grooves etched into the material. Sometimes call these lines. All right. The spacing for these screws is usually described like this. We usually describe them as the number of lines per certain distance for example, I have a diffraction grating right here. It just looks, it's a little piece of cardboard with some plastic in the middle. It's like a slide, like you would put into a slide projector like they used to have. And it says on there that I have 1,000 lines per millimeter. So for example, here I have a sketch of a diffraction grating with 10 grooves over its 1 centimeter of width. So if you imagine that this is 1 centimeter, of course it's not, it's several centimeters. And then I have 10 separate lines on this. So this grating would be described as having 10 lines per centimeter, or 10 grooves per centimeter, however you want to think about it. So 10 lines per centimeter. All right, to calculate the position of the bright and dark fringes, you need to know the distance between the grooves, and for the above grading, the distance between the grooves is going to be, we had 10 lines per centimeter. I want to know the number of centimeters for a single line, so I'm going to take the inverse of this, and so that's going to be 0.1 centimeters per line, or the distance between them is just 0.1 centimeters. Now, of course, we'll deal in the SI system, so anytime you see centimeters or millimeters, I'll need to convert that into meters. All right. So, for example, here's a good question just dealing with this. I'll stop there and pick back up with this.